Hello, class. Welcome back for another lesson. We're going to continue our discussion of polar coordinates in lesson 9.1. This is day 2 of that lesson. We're actually going to spend 3 days. Originally, I was just going to cram everything into day 2, but it was starting to get a little bit lengthy, so I think we'll just split this up over the course of 2 days. So today, we're going to focus on 2 tasks. First, we're going to convert polar coordinates to rectangular coordinates, and then we're also going to convert rectangular coordinates back to polar coordinates. So if you have not done the lesson on graphing polar coordinates and kind of thinking about what polar coordinates are, I would do that first. We're kind of starting with the assumption that you know a little bit about polar coordinates from the last homework assignment. Before we get started, I wanted to give you 2 equations that can help us out quite a bit today. This says that if P is a point with polar coordinates r, theta, and also shares the rectangular coordinates x, y of the same point P, we can say that x equals r cosine theta and y equals r sine theta. Now, this might be new equations for us, but they're real easy to understand why they work. If we look at the next slide here, so here's our point P, just some random point floating here in the first quadrant. And if I were doing rectangular coordinates, I would say over x and up y, so the coordinate of point P would be xy. Well, we learned from the last lesson that we can also express that as a polar coordinate. And you might recall that a polar coordinate we write in terms of r and theta. So it's the exact same point, it's just 2 different ways of expressing that coordinate. So we can express it over x and up y, or we can express it as the angle is theta, that's the direction, and then r is how far you go. That's how many units we travel in that direction to get to point P. Okay, so just 2 ways of describing the exact same point. And so why do these 2 equations work? Well, if we look at angle theta and kind of focus on that, if you think about our SOHCAHTOA ratios, we know that cosine theta is adjacent over hypotenuse. So in this case, the adjacent is x, and the hypotenuse is r, so cosine would be x over r. And then if we just multiply r on both sides, we get x equals r cosine theta. So that's where that equation comes from. And then the other one, again, focus on that same angle theta, and we know that sine is opposite over hypotenuse. And so the opposite in this case is y, the hypotenuse is r, so we can say sine theta equals y over r, and then y would equal r sine theta. So keep those 2 equations handy. We're going to use those quite a bit over the next several examples and possibly even over the next several days. So here's part 1. Originally, again, this lesson had 4 parts to it, but I decided that we're just going to look at parts 1 and 2 today, and then we'll look at parts 3 and 4 on Wednesday. So part 1, we're going to be transforming a coordinate that's in polar coordinates into rectangular coordinates. So here's our first example. The coordinate is 3 pi over 2, and that's currently in polar coordinates. And we want to convert that to rectangular coordinates. We want an x and a y value. And so I've already got us started here, so we're going to use those 2 equations. To find the x value, we're just going to multiply r times cosine theta. And to find the y value, we're just going to multiply r times sine theta. So in this case, we're given both of those values, right? 3 is our r value, and pi over 2 is our theta value. So we have all the numbers we need here. So we're going to say x equals 3 times cosine pi over 2, and y equals 3 times sine pi over 2. And so fortunately, these are values we know. Pi over 2 is a friendly angle that's on our unit circle. So we know the cosine of pi over 2, or 90 degrees, that is 0. So x will just be 3 times 0, which is 0. And then y equals 3 times sine pi over 2. And we know the sine value at pi over 2 is 1. So y equals 3 times 1. So y will be 3. And I think the best way to express this answer when we're all done is to write it as a coordinate, since that's the goal here, is to express this as a coordinate 0, 3. And that's our answer. Now, this next part I'm going to do is not required, but it might just kind of help you see the connection or why both of these are the same coordinate. We know how to graph 0, 3, so if we just draw a quick sketch here, we know 0, 3 means to go left to right 0 and up 3 units. And then if we think of that in terms of polar coordinates, it says the angle is pi over 2, so that just means you go 90 degrees from your polar axis, which is kind of like your x-axis pointing towards the right, and our pole is the origin. So if the direction is pi over 2 and r is 3, that just means you travel 3 units in that direction. So if I count 1, 2, 3, that puts me in the exact same place that 0, 3 puts me. And so again, those are both the exact same coordinates. They're just expressed in 2 different ways. It's the same location. Here's our second example. It says convert -2, 3 pi over 4 to rectangular coordinates. So same kind of deal. I got us started here. So x equals -2 times cosine 3 pi over 4, and y equals -2 times sine 3 pi over 4. So again, these are values that we know from our unit circle. So we shouldn't need our calculator here. We know that, here, let me switch back to blue. We know that cosine 3 pi over 4 is in the second quadrant, right? 3 pi over 4 is going to be over here, so the cosine is going to be negative, and that's one of our common values. It's going to be negative root 2 over 2. All right, so then we can multiply those two together, and we get 2 negatives is going to make a positive 2 root 2 over 2, which simplifies nicer to just root 2. I think would be the best way to express that for x. And then for y, we'll just do the same thing. So we have -2 times sine 3 pi over 4. So if I look at that angle, I'm in the second quadrant, so sine is positive over there. So this will just be positive root 2 over 2. And same thing, I think those 2's will cancel out nicely, and this time the negative does not cancel since there's only 1, so I have negative root 2. And then again, I think it's best practice when we're all done to go ahead and write that as a coordinate, since that's what the question is asking. It wants us to express this as rectangular coordinates, so I think it would be appropriate to put it in that form, using parentheses and a comma. Okay, here's our next example. The polar coordinate is 7.5 and 110 degrees. So this one you'll notice is a little different because 110 degrees is not an angle that's on our unit circle, not one that we're familiar with. The setup's still going to be the same. We'll still do 7.5. That's the r value times cosine of the angle. And in this case, we don't know what cosine 110 is, so we're just going to grab our calculators. Since 110 is in degrees, you want to make sure your calculator is set in degrees. And so just multiply those together is all you need to do. You get -2.57 for x, approximately. And then for y, same thing, just multiply 7.5 times sine 110 on your calculator, and you should get about 7.05. Again, it's best practice to go ahead and write that as a coordinate when you're all done. Also, I didn't do this on the last example like I did on the first one, but if you want to see a sketch of what this looks like, just to see if it checks out and see if your answer makes sense, -2.57 up 7.05 is going to be over a little and up quite a bit more. And that's going to give us an answer that's, or a coordinate that's in the second quadrant, clearly. So if we go back and look at the original and we want to know, does that agree with the original? Well, 110 degrees does point about, it seems like, where that direction would be, clearly in the second quadrant, and it asks us to go 7.5 units in that direction. So this checks out to me. It looks like both points are in agreement that it's going to be landing right in the same place like we want it to. Here's one last example for part 1. It says convert 6.3, 3.8 to rectangular coordinates. Now, when you first look at this, you might say, well, wait a minute, this looks like it's already rectangular coordinates. Both of these are numbers. I don't see an angle. I think, despite what it looks like, I think if this is in the directions in the book that says polar coordinates to rectangular, we have to assume that these really are polar coordinates. And I think they are. We just have to just be careful about how we think. This can still be our r, that's okay. And I think this can still be our theta. And you might be thinking that there should be a degree sign or a pi or something like that if it were in radians. But you might remember that many times when we talk about angles, we do talk about radians. And sometimes we have radian measures without a pi attached to it. Okay, and so I think that's what's happening here. And I think you're going to see an example or two like this in your homework, where it looks like this maybe isn't an angle, but I think it is. It's just saying 3.8 radians. And I think to me, it's always helpful if I kind of draw a sketch. I like to use pi as my reference if I want to know where this angle is. I know that pi is about 3.14, so 3.8 is going to be a little bit past pi down in the third quadrant. And so I think that just gives me kind of a visual of where this coordinate is and might help me make sure my answer is correct here in just a moment. So even though it's in radians, we're still going to use the same formula. We're going to say x equals 6.3 times cosine 3.8, and y equals 6.3 times sine 3.8. A quick alert here, since this is in radians, we need to make sure we change our calculators to radians. Be careful in today's assignment. You might find yourself changing your calculator back and forth from degrees to radians quite a bit within the same lesson. So just be aware of that. Switch your calculator to radians. And when you do that, I got negative 4.98 for x, and for y, I got about negative 3.85. Again, I think it's good practice to go ahead and write that as a coordinate. Also, if you want to just kind of do a little sketch again to kind of check to make sure your answer agrees with the original. We know that negative, this is close to -5, this will be close to -4, so that's going to take me down here in the third quadrant. And if we go back and look at my original picture, we said that 3.8 radians would also be in the third quadrant. And since r is positive, it'll go in that direction further out into the third quadrant. So I think that checks out okay. I think we're good. All right, so now we're ready for part two. Part two, we're going to change rectangular coordinates to polar coordinates. And to do that, the textbook lays out a three-step process to help you do that. And I think this is a great process. I think it's a great suggestion by the book, so I'm going to offer it to you as well. And step one, they want you just to get a visual. I think that can really go a long way. If we know where the coordinate's going to be, that's going to help us a whole lot when we're determining what the r value and the angle, the theta value is going to be. So I think that's a great suggestion. The more you practice these, maybe you'll find that you can skip step one. But as you're just starting out, I think go ahead and plotting the point is a great idea. Step two, we have to figure out the r value, and we can do that real simply by using this equation, r equals the square root of x squared plus y squared. So let me skip a slide. I'll come right back here, but I want to show you why that is. It's very easy to see. So if x is the distance along the x-axis and y is the vertical distance or vertical change, and we've been saying all along that r is the distance that we travel in the direction of theta. So that being the case, r is acting kind of like our hypotenuse of this right triangle that we see here. So because of that, we can say that x squared plus y squared equals r squared. Or if we simply just want r, we can say r equals the square root of x squared plus y squared. Okay, so we're going to use these, probably the second formula here as we do the second type of problem here in this assignment. However, I'm going to kind of highlight these or put a star by them. We're actually going to use these in tomorrow's lesson as well. So keep these handy. Both of these equations can be quite useful to us moving forward. So anyways, that's what we're going to do in step two. That's going to help us find the r value. And then step three, we need to determine the theta. And there's actually two ways we can do that. We actually can go back to step one. You might be wondering, why did I plot the point for? Well, sometimes when we plot the point, it's going to be a very obvious location that we'll know theta without doing any further work. For example, if I had the coordinate, let's say like -2, 0, well, I know that points to the left 2 units, and that would have an angle of pi, right? It's kind of going to the left, the negative side of the x-axis, and that's where pi is. And so sometimes you might get some of those quadrantal values or some other values that we know from the common places on our unit circle. So sometimes that sketch will allow you to do that. If that's not the case, if the value is not a common value or a common location, then we can use this backup, which is tangent theta equals y over x. And that's a ratio we've been using for a long time now, the last several weeks or months even. Tangent is opposite over adjacent, or if we look at the triangle, the opposite will be y and the adjacent will be x, and so we can also call that y over x. And so if we know the x and y value, not only can we find the r value in step 2, but we can also use x and y to find the angle. If we know the tangent equals y over x, we can use the inverse tangent button on our calculators to work backwards and find that angle. All right, so here's our 3-step process. I'm going to take you through a few examples here, and we'll wrap up part 2 of today's lesson. All right, so here's our first example. We're going to start with kind of an easy one. It says convert 0, 6 to polar coordinates. So we can assume that this 0 is our x value and this y, or this 6 is our y value. So I'm going to take the book suggestion and just make a little sketch for us, which I've already done. And so remember, we're just trying to find an r value and a theta value. So if we can find both of those values, then we're in business. And so this one is probably simple enough that we can do without even really going into step 2 or 3. This one's so easy that you can kind of just look at the picture and tell. And so the r value, remember, is if we're pointing this direction, this is our polar axis. And so since our point's up here, that means we need to travel this direction 90 degrees or pi over 2. So that's going to be our theta value, pi over 2. And then our r value is really easy to see. If you go back and look at our directions here, it says to use the Pythagorean theorem to help us out. But in this one, it's so easy that we don't really need to do that. We can just count up 6 units. Okay, we don't need the Pythagorean theorem to tell us that we're going in this direction 6 units to get to that coordinate. And so that's our r value is 6. And so if you want to write that as a coordinate, we express the r value first and then the angle second. Okay, so sometimes these problems will be much easier than others. This is one of those cases, but we're going to progress in difficulty here in just a minute. All right, here's our second example. It says convert 1, -1 to polar coordinates. And so I went ahead and drew a sketch here for us. So we're going to go over 1 and down 1. And so again, we need to find the r value and we need to find the angle. So this case, the r value is a little less clear. And so we are going to go ahead and use that formula. R equals, we're just using the Pythagorean theorem. So we're going to have 1 squared plus -1 squared. So both of those give you 1. So 1 plus 1 is 2. So r is going to be the square root of 2. So we're halfway there. Now we just need to know this angle, and this is one of those ones you can use your inverse tangent button if you need to, but this is actually a value that we should know from our unit circle. Notice both the x and the y distance are the same, and so if that's the case, that's going to be our 45, 45, 90 triangle. Is that correct? And so I think that tells me that theta is going to be either -45 degrees or pi over 4, -pi over 4, that is. Okay, I think my tendency, and I think if you look at the examples in the book, they're typically going to use radians most of the time. So if you want your answers to match, I would probably stick with radians. So we put our r value first, that's going to be √2, and then our angle, which is -pi over 4. If you did put square root 2 and -45 degrees, that wouldn't be wrong. Likewise, if we go back to this example, someone might put 6 and 90 degrees. Again, that wouldn't be wrong, but I think we tend to like to, in the more recent lessons and chapters, we've been using radians more often than degrees. And so hopefully I've convinced you that radians are a good way of expressing angles. So again, it's not wrong if you do degrees, but that's usually the way I'm going to go. And I think that's the way your textbook will tend to go as well. All right, so here's our next example. The coordinates are 1.3 and -2.1, and they're telling us to convert to polar coordinates. Now you might be wondering, like, hey, didn't we have a problem like this a little while ago that looked very similar to this, but you were telling me it was already polar coordinates. So how am I supposed to know if it's polar coordinates or rectangular coordinates, like is negative 2.1 y, or is it the value of the angle in radians? I think you just need to use context clues. So the directions here make it clear that we're changing to polar coordinates. So that means this must be rectangular coordinates. If there's ever not enough context and you're showing work in your homework or whatever, it might not hurt to write radians if you are doing radians and it doesn't have a pi value attached to it. But again, context clues can go a long way. So anyways, I went ahead and drew the sketch. So I know I'm in the fourth quadrant down here. Step 2 says to find the r value. So again, we'll just use the Pythagorean theorem to help us do that. I'm going to do 1.3 squared plus negative 2.1 squared. And feel free to use your calculators to help you do that. And when I did that, I got a value of about 2.47. And so that tells us how far we travel. And now we want to find the angle. So this is the first example where you'll notice the angle is not obvious. Okay, it's not one of those common values on our unit circle. And so this is where, if we go back to this step 3 here, it says determine the angle. And I wrote to use the inverse or use tangent if necessary. So I think this will be an example where it's necessary since we don't know what that angle is. So we do know that the tangent of that angle is the opposite over the adjacent, or y over x. So it's going to be negative 2.1 over 1.3. And to do that, we're going to need to use our inverse tangent button. So hit the second key with tangent and put those numbers in there, and that's going to be your theta value. So this ratio goes right in there. And then I guess you want to think ahead, like, do you want your answer to be in radians or do you want it to be in degrees? And so I suppose, whatever you choose, just make sure your calculator's in that setting. I'm going to go ahead and give a radians answer. So when I did this, I got theta is about negative 1.02 radians. I'm going to make a little note there that it's radians. If you did yours in degrees, you would have got negative 58.2 degrees. So again, I don't think one is right or wrong. I think, again, I tend to favor radians, and I think your book will do the same. So you might see my answers that I provide for you in radians. Either way, when you're done, if you could write your answer as a coordinate, just like we were on the other examples, I think, again, that's good practice to continue. Also, when you're done, it might not be a bad idea to just look at your original sketch and make sure it checks out. So negative 1.2 radians is going to take me the reverse direction. And then if I go out 2.47 units, I get to this coordinate. And so it looks like I'm in the right quadrant. Everything appears to be okay. So that leaves me feeling confident to go on to the next problem. All right, here's our last example. If you've stuck with me this long, thank you. Hang with me just a little bit longer, though. There's something a little bit tricky that happens on this one that has not happened yet. So if you can hang with me, we'll wrap that up and we'll be done. All right, so again, I started with the suggestion of drawing a sketch. This one will definitely pay dividends for doing that here in just a minute. So I guess the next thing I'll do is find the r value using the Pythagorean theorem. So that's negative 3.4 squared plus 0.27 squared. And type all that into your calculator. Don't forget to take the square root when you're done. And when I do that, I get approximately 3.41 is the number that I'm getting. Okay, so we're halfway home. Okay, then we want to find the angle theta. So again, this is not one that is common to me. I can't look at these numbers and know what the angle is. So we're going to use the inverse tangent again. So we're going to say the inverse tangent of y over x. So that's 0.27 over negative 3.4. And so again, for your calculator settings, just think about what kind of answer you want, whether you want an answer in radians or degrees. So again, I'm going to go ahead and stick with radians for now, and when I do that, I got a theta value of about negative 0.079. So it's going to be a pretty small angle. If you want to do degrees, I did that as well, and I got negative 4.5 degrees. Okay. All right, so we have a small problem here. This is what I was alluding to a minute ago. If we think about these angles here, whether it's negative 0.079 radians or negative 4.5 degrees, those are angles that are pointing into the fourth quadrant. And that does not agree with our picture over here. If our R value is positive 3.41, that's going to take us in this direction over here. Well, we really want to be in this direction over here. And so let's first figure out why, like, did we make a mistake or what's going on here? And I think what's going on is if we travel back in time to an earlier lesson, you might remember that when we do inverse tangent, think about what our range or our output can be. You might remember the range for inverse tangent is negative 90 degrees to positive 90 degrees. And so what that means is it's when I hit the inverse tangent button on my calculator like we did here, that's either going to give me an answer that's in the first quadrant or it's going to give me an answer that's in the fourth quadrant. Okay, either a positive answer up here or a negative answer down here. And so that's my range for this problem. Well, the issue is that my angle's clearly over here in the second quadrant. It's out of range. So you might recall that there's actually two angles that have this ratio, right here for its tangent. One is found here in the fourth quadrant, the other one is over here in the second quadrant. And the good news to us is that we know the difference between those two angles is 180 degrees or pi radians. And so if you ever see that happening when you're doing a problem like this, that your sketch that you drew, like the direction that you're going, disagrees with the angle that's given, when you hit the inverse tangent button, you just have to outsmart your calculator and add pi or add 180 degrees to get over in the correct quadrant. Okay, so if I'm doing my radians answer, I'm going to add pi, and that's going to give me an answer of about 3.0. Or if you're doing degrees, you can add 180 degrees. And that's going to give you an answer of 175.5 degrees. Again, when you're all done, go ahead and write your answer in coordinate form. So 3.41 is my R value, 3.06 radians is my angle. If you put 175.5 degrees in there for your angle, that would be okay too. Okay, so major, just kind of red flag alert, something to be thinking about. Anytime you're using the inverse tangent button, look at your sketch, and this is one of the reasons they ask you to draw that sketch. The book suggests that as your first step, is when you're done, you want to look at your answer and make sure that the angle that your answer is giving is in the correct quadrant that your original sketch. And if not, you probably need to add pi or 180 degrees to get it to the correct quadrant. And again, the reason that happens is because the limited values that inverse tangent can give you. Okay, so just kind of keep that in mind. I'm certain that's going to show up at least on one problem, if not maybe a second or third problem in your homework. So just be aware of that and keep your eye out for that. Speaking of your homework, here's your assignment for today, page 585. I'd like you to start with number 42 and work your way to 68, counting, just doing the evens in that section. So good luck with that. Tomorrow we're going to continue one more day in lesson 9.1. We'll do parts 3 and 4 that I mentioned. As you can tell, this video is getting kind of long. We're almost up to 30 minutes, so I didn't want it to be longer than that. And so we'll just save that for tomorrow as we change polar equations to rectangular equations and vice versa. So we'll have that to look forward to in our next lesson. I guess not tomorrow, Wednesday. Until then, good luck. If you have any questions, please feel free to reach out again via email, message, If you need to get on and do a Google Meet, just let me know. I'd be happy to do that and help you in any way I can. So hang in there. You guys are doing a great job. Keep up the good work.